And the first presentation comes from François-René Lachapelle from Photon, is the company called. And he will give us a talk about autonomous mineral data logging using a broadband hyperspectral imaging system. So, François, the stage is yours, and we are looking forward to your presentation.
Thank you very much. So hello, everyone. As I said, I'm François from Photon, etc. in Montreal, in Canada. And I'm glad to present you our new nCore autonomous mineral data logging using broadband hyperspectral imaging. So first of all, who we are. At Photon, we're a multidisciplinary team of scientists, physicists, technicians, with a very wide range of specialties and very diverse skills, and we are working on complex solutions for engineering in the industry, but also in the academic and very broad applications. So today I'm presenting this in mineralogy, but we have a wide range of applications as well. So a little background story where we come from. So we were founded 20 years ago now, when the president, Sébastien Blais-Ouellet, who's here today also, was working on his postdoc at Caltech University in the United States on volume Bragg grating. So he patented this tunable filter based on volume Bragg holographic gratings. And he brought this technology back with him in Montreal. And actually, this is still a core product that we sell at Photon. So it's a tunable filter that can be put in front of a laser to do a tunable laser source or in a laser line. And you can also put it in front of a camera. So then you get an hyperspectral camera, but scanning in the wavelength dimension. So every step, every frame that you take, it's at a different wavelength. So this filter is very effective in the visible, the near-infrared, but also in the short wave up to 3 microns. So, and it's very narrow band, so we needed very powerful cameras in the infrared to take full use of this filtration technique and hyperspectral technique. So we were looking around, and we decided that the best way to get this very efficient, very sensitive camera was to build our own. So we decided to go in the business of SWIR camera and SWIR imaging and hyperspectral camera. And from this, we spun off a few companies, Photonic Knowledge in the mining industry, Optina Diagnostics, that's a company that does retina hyperspectral imaging and clinical optics, and UView camera, they do EMCCD camera in Montreal as well. And so these filter, the hyperspectral cameras were also very efficient in microscopy. So we have a lot of partners in university around the world that are using our hyperspectral systems in microscopy and diverse applications. But then the infrared camera in itself, it's very useful for the industry, as you know, for quality assessment, for sorting, for waste sorting, plastic analysis, and all this stuff. So we are building this business of infrared cameras, but we also have this preclinical imager, because our cameras are deep cool at -85 degrees, so you get very low background noise. So in the shortwave infrared, there's a transparency window in living tissue that allows to see through it for a certain depth. So we have exploited this in this mice imager that we call IR Vivo. So you can put a mouse in it and inject it with dyes and see it process live through it with our infrared cameras. And the last but not least project that I want to talk to you about is the partnership that we have with the Canadian North Atlantic College of North Atlantic, CNA. So it's a university that does work with the mining, close with the mining industry. So they're good in geology, and they had this project that they approached us for, and it's a core logger. So drill core of 3 inches. They wanted to get the most info in one single passage through a machine. And so we have this capacity with a very diverse team of engineers to go from the clean room and packaging detectors and doing cameras and go all the way into a very evolved system like this one that I will show you today. So just a quick recap on what we're doing at Photon currently. So we have advanced material. That's one of our big business in photovoltaic materials and nanotechnology in university mainly, but also in production. In life science, as I said, there's the mice imager, but also nanoparticles that are very useful in drug development in life science and in the industry. So of course we have the mining industry, but as I said, all this plastic have a very strong signal in the SWIR infrared and sorting industry and everything. So this is, well, it's in Canada, so there's snow. But this is our nCore, as it was very clean before it was moved into the mining industries. So it's a fully equipped lab within a container, 20-feet container. So you can see my colleague here is adjusting, is feeding it with drill core boxes, and it's very fast scanning. So it's super efficient. One passage, you can assess the quality of the data, and you have, on this device, you have 5 hyperspectral cameras with their own dedicated illumination, depending on their wavelength. So it has more than 1,000 wavelength bands that can be scanned at the same passage. And so you can see we are going through this machine. There's a laser 3D profiler to assess the quality of the core, the rocks. And then you have this U-shaped container that brings back the box at the entrance, and it allows you to be very flexible and add on new equipment and new devices. So it's very modular system. And then, as you saw, it can fit onto a truck and be shipped directly on site because there's a very sensitive data that can be acquired. So if you don't have to ship your sample to a lab, then you're saving a lot of time. In this industry, it's gold. So just coming back a little on reflective spectroscopy. So when light hits any material, it interacts with it. What we can see is an integration of the visible spectrum. But if you have the right spectrograph, then you can see really the spectral signature. So every material has a unique spectral signature, but it doesn't mean that you're able to discern different sample if you're using only the visible light. So we are adding 5 different devices to go from 400 nanometers all the way in the long wave at 11.5 microns and get full spectrum with very high resolution in order to be able to discriminate different, for example, here this is different rocks, or minerals, I should say. So, as I said before, we had this very efficient hyperspectral filter that was filtering in wavelength dimension. When you're on a conveyor, that's not the most efficient way to work. So we developed a push broom, which is it scans a line of pixels, and then it takes a spectrum for every line of pixels. And when you go through on the conveyor, when you go through this beam, then you get the full image in hyperspectral cube. So you're scanning in the spatial dimension. We called it the Helios, and it's a fully reflective Opner spectrograph, so we get a very good throughput. We also do all of our optics in-house to make sure that we have very good throughput for the sphere. It's very important because we have extended sphere, almost to 3 microns. So in this range, lenses are a tough business. So as I said, we do a lot of vertical integration. We go from the camera to the LEOs, which is the spectral part of the camera, and then we can put it on this multi-sensor platform and integrate it in a full lab. Of course, you can stop us at any steps along the way and have a custom device made for your application if it suits. So just a little bit more about this compact device. So the first step would be the LEOs on a benchtop with a small translation stage, custom illumination depending on the depth, field depth that you want and your illumination of your sample. But then we have this compact that is linear scanner with up to 5 different sensors you can combine. The U-shape is the one that you saw earlier that fits into the container, so you can have up to 14 different sensors. It could be lifts, libs, X-ray, other stuff. Think about it, and we can put it in and make it work. So what are the normal, typical hyperspectral sensor that we integrate in this field? So we have this VisionSTR, that's one camera. Then the sphere part is our specialty. So we split it into 2 detectors, one InGaAs and one MCT, to get the most out of it. So the sphere InGaAs goes to 1.7 microns, and the E-sphere to 2.8 microns, and then mid-wave, long wave, and as I said, a bunch of other stuff like the tripod, because actually you can pick out one of the camera and scan, put it on a tripod and pan scan your mining walls. So time flies. I'm just going to skip through some. This is a very filled slide. If you want to have more details on the very specific, come see us at booth G21, and I can give you more information on what are the options for this kind of machine. So there's a lot we can do in the mining industry with such a wide spectral range. But also, if you have any sample and you want to see, not in the mining industry, but in any industry, you have any sample and you want to see what signature, what we could get from this kind of analysis, just contact us. We can do tests in the visible, in the sphere, mid-wave, long wave, and see what comes out of it. It could be vegetation, indices, water, hydrocarbon, plastics, remote sensing, and a lot of things that can come out. And we will find the right sensor for your application. I just wanted quickly to show you real data. So this has been split into different bands, but they are actually false color of the core boxes that you saw earlier in the RGB, VisionSTR, sphere, MWIR, and LWIR. But the point that I want to take out from this is that these are actually data cubes. So if you scroll your mouse over this, you would get one single spectrum for every pixel on this image, from 400 nanometers up all the way to 11.5 microns. So we produce the data, we clean it, because we have a lot of expertise in cleaning those kind of data. And then we feed it to the geologist that works with us at the university. And then they can assess and spectrally classify what's in it. So this is the classification that they would produce afterwards with a bit of AI also. And this, when I was preparing my presentation, it made me thought that another application that I did with the LEOs is with the 2.5 micron. So we flew over field, forests, lakes, and roads, and we were looking for oil spills. Thank God there were none on this, I reassure you, but that's just to show how broad of the application we can get with this kind of devices. to wrap it up, so why you should choose Photon? We have a strong team and a very diverse team of scientists that work with very diverse expertise, and we can do vertical integration in many fields, and just contact us and see what we can do for you. We are at booth 10G21. Thank you.
Thank you very much. First question. Who buys a truck of spectral imaging devices from you?
A truck? Well, the
or
truck was
a container.
The container didn't come with its own truck.
Okay.
Yeah, but actually it was directly the university that had grants to buy this kind of lab equipment, but they wanted to bring it directly in the field. So yeah, that's our client was the partner also at CNA, and that's how we just. We wanted to present this today because it's a big, impressive machine. So it's really showing how we can really vertically integrate from the clean room to the garage to the mine and go along with our clients in this journey.
Sometimes you get a laptop as an addition to when buying a device. Think about to make the truck as an addition to the container. Maybe that's a good feature.
Does it come with the driver also? Because it was quite a trip from Montreal to the Labrador.
Yeah. So very impressive. Are there any questions? Because the colleagues showed so much know-how, especially when they talk about the data cleaning and bringing everything together. That was really impressive. Think about that you saw an imaging system from VIS to nearly MVIR.
Yes.
So a lot of technology. So then, therefore, I'm asking, can you say a little bit more? What kind of methods do you use to bring the data together? And how big is the data for one acquisition through the whole imagers from VIS to MVIR?
That actually is a very good question. That was a big concern for us and for our clients, because they want to scan a lot of data, like kilometers per day. So it's very efficient. As I said, it's quite fast. We managed to make 1.6 kilometer really fully scanned in one 8-hour shift. Oh. But then the data, the raw data is a little bigger, but then we pre-clean it down to about 250 megabytes per meter, which is quite manageable for the full extent of the 1,000-something bands. And then you feed it to an AI who sort it out further, and then you get identification of minerals.
Okay, and do you do some kind of compression to store the data afterwards? So
at this point, it's beyond what I'm personally doing. I'm the physicist in this company, but then I would have to talk with the data engineers. Yeah, okay. But they basically, you have to identify what's important, and just spatially, there's a lot of loss because you have the box and the rest of the container. So just cropping keeps you, gives you like quite a data reduction already. And then for the rest, I would have to forward this question to my colleagues. Sorry.
Okay. If there are no further questions, then we've done this. Thank you very much.
Thank you.